Okay. So today, no, we'll start with the skip gram problem. Is that fine with all?
Yeah, really would be interested.
Yeah, let's start with skip gram. I see one example taken in the class. So I'm referring Professor Monali's lecture. Okay, let me see. Somebody is waiting. Shankar is waiting. Okay. You guys also able to. You are also able to admit, right? Is that option coming for you also there?
Yeah, it's coming.
Oh, okay, okay. In case I don't see.
Yeah, we'll admit them. Yeah.
Sure, sure. Thank you. Okay, so let's get started uh, for the skip gram. Do you want me to take that theory part first, or because this is directly the example is given here in this slide?
And we can go ahead with the example, I think.
Okay, let's start with the example. Oh, they haven't given anything on the here. Okay, here we can see. Where is this corpus, right? How did they form the? Okay, I think it's not given here.
There was a detailed solution yesterday posted in the group NLP for this sum.
Yeah, that is also given.
Step by step, yeah.
It is the same thing also, right?
Same. It is exactly the same.
Yeah, I'm just opening that one. 1 second. Because I have gone through that lecture yesterday. Also, it was very well explained by Monali ma'am too. Still checking. Okay, I see now. See, I'll just save and open. Yeah, I think Aditya, yeah, I'm opening the attachment Aditya shared. Aditya, you are on the call?
Yeah, hi. I just joined.
Oh, okay, thanks. Yeah, thanks. I'll open that attachment too.
Yeah, sure.
Yeah. Yeah, it's here. Let me open that notepad also just in case required. Okay. Here need is the center word, right? In this example. Oh, it's given here. It's
Yes, exactly. What I did is basically look into the example shared by this Chitna ma'am, the last example that she shared. No?
Yeah.
So
The same thing.
yeah,
Same thing,
I
right? It's the
just
same thing. Yes.
yeah, exactly. It's just the same thing.
True.
So what I just did is you can see the given data I just wrote clearly, like what exactly is the given. So if you scroll up a little bit, so I give them information about what is the window size, what is the learning rate, and what are the positive pair of words that we have. So you can see like we have like k equal to 3. So because we have 3 negative words for the given target word. So k equal to 3 because we selected target word equal to net, and k3 means we need to select 3 keywords for each selected target. So that is Pimples, Zebra, and Idiot. So these 3 words they already selected those, and these are the initial embedding metrics that they already given to us. So the point was like why we use skipgram is we need to have an updated weights for target word that is embedded matrix. So the first row of embedding matrix we need to be updated one for net, and the all rest of the words from context word excluding the first row we wanted to be updated for context matrix for the other words like star, pimples, zebra, idiot. So for these last 4 rows for context we need to get updated.
Yeah.
So that's the whole purpose of this skipgram.
Yes. Everybody is okay with this, or any more input before we start on the solution? I mean, Aditya has explained the background, what is given, and what we are trying to achieve here. We are just trying to build the embedding matrix and the context matrix actually.
Yes, embedding matrix first row for NED, the target word, and the context row, excluding the first row, everything in context matrix.
Yes. So here we have a window which is like 2, and then the context word is, see, the need is the center word. So the current word need is the center word. The positive word is stark, right? And these three words, pimples, zebra, and idiot, are the context words. Everyone is aware of this one, or should we go back to that PPT? Because we need to form the this one, right? Training set also, right? First, did you put that also here? I think you did directly put the equation, right?
Yeah, I directly went for the equations.
I mean, I know complete solution, but how about others? Or if we needed, we have to go back to we first build the training set, right? Like we take one example of positive context word, right? And then 3 examples of negative context word.
This one is given initial embedded matrix.
Yeah.
Actually, you are right when to understand the concept.
Yes,
Yogesh.
yes, yeah.
So here only one thing missing is corpus. What is the corpus of the statement given?
Yeah.
That one line we can add in this. Like corpus is, I think, Netstock is the most honorable man. So that's the statement. Corpus.
Correct. Let me see if it is there here, because I remember it was.
It is there in the example. The corpus is given. First one.
First one. Yeah. The Ned Stark is the most honorable man. Yeah. Okay. So if you see here, okay, let me open that one also, because I wanted to show that thing first, right? Because when we select the one pair, right, the center word and the positive context word, we take it the target as 1, right? And for the 3 negative context words, we set the target 0, right? Everyone is aware with this, or still let me open that 1 second. Skipgram, right? It is somewhere here, right?
Here.
Yeah, here. Yes. I'm just trying to check that initial setup, right? Like context word and this pair.
If you want to specifically look for that particular example, I just pasted a link in the chat. That is from where our teachers has took this example.
Okay. Yeah, I'll take that one too. Okay, 1 second.
No, just above only, Yogesh. I think you already. This is about object rules. Little above, little up, little up. A bit more actually. A bit more.
Here somewhere, yes.
Here. If you keep here, when we say window size, when we take plus or minus 2, apricot being the target, right side 2 words and left side 2 words will define the window.
Yeah.
And within the window, tablespoon, off, jam, these 4 words becomes the positive context words.
Yes.
And target will be 1 for that. Given the apricot is the target, the 4 context variables will be the 1. And we choose negative examples. For each, generally that k equal to 2 or k equal to 3 means for each word at least 2 negative samples they will take. So these words can be random. The negative examples can be random. Or you can say from the corpus also we can take like lemon is a negative context when it is apricot.
Yeah.
Pinch is also a negative example for the apricot when apricot is the target, because pinch is in the corpus but it is outside the window context. Context window. Yes.
So yeah, we have to take one example of the positive context. So here we have taken like all 4 to show, but in this case, in our case, so to build the data, right, for the training. So this is our center word given, right, NED. So let's take NED and the first positive context word, which we can take anything within this 4 context word window, right? Plus 2.
No, their 2. Window size is 2 only mentioned in the question.
Yes.
So that in the question.
Yeah, and also they have given the context word also in that. But if it is not given, we can check, right? Because if you see in this context corpus, they have mentioned the center word as NED, right? Oh, they have given actually, because you see the corpus is the current word. This is the given actually. So Ned Stark is the given one. So we can see the Stark is the positive context word, right? So this is what first thing, like Stark. So generally when we start the setting up the self-learned train data, we pick up the center word and one positive word, and the target we set it as 1 because it's a positive context. And they have given in this example k equal to 3, right? It means for each one example of the one pair of this center word and positive context, there will be 3 negative context word pairs, right? So then we set up like a same center word with the 3 negative words here. So pimple, zebra and idiot. Pimples, then this is just to give a background. So Ned and idiots, right? Okay, so any 3 words we can pick, but they have given the 3 words k equal to 3. So we have taken the 3 examples of the negative context words here like this, and for them we set the target as 0 because they are negative words, right? And then so this is our start thing, and then with the one hot matrix, what we get in the corpus, we will have all these words, right? In a corpus, we will have all these words, but every word has it somewhere in the list, right? This is index, so Ned is in some index. So for that particular row, we are representing by value 1. For remaining, everything will be 0. Similarly, for say Stark, some particular row where that Stark word comes, so that is the 1, and everything remaining is 0. So this is one hot matrix we have with us initially, right? And these two are the matrix given, or we can start with some weights. For each word in the vocabulary, we will have its embedding entry and the context entry, because the same word can be the center word, also it can be the context word as well. But I remember ma'am mentioned that we can use the same one, but I think generally they keep both these two different.
Yogesh, actually this skipgram, right? It learns these two actually: embedded matrix, embedded weights, as well as context weights. The learnings are 2. It's a self-supervised and self-unsupervised learning.
Yes.
It learns 2 embeddings.
Oh, then we have 2. Okay. Yeah.
Being it as embedded and being it as out. Actual output is whether to find whether the context word is within the context or not, and also it learns the weights.
Yeah. And our goal, as even Aditya mentioned, right, our goal here is not to find the whether we have the target matching, but to build this weight correctly. So based on the training data, we can like update the weights in each iteration, and at the end what we will have is the final embedding matrix and the final context matrix, right? So here, so we have some initial values here, okay, for initial values of the embedding as well as the context matrix. So assuming that will go on, okay, let me refer his period. He has calculations, right? Yeah, he has started here. Okay, oh, you did directly the multiplication. Okay, let me. So we have that formula, right? Somewhere.
Which one?
Yeah, I'm just trying to open that. 1 second, I'll show you here itself, I guess. That small table is there, right? Weight and this one. She took one some example, right? There's some. No, this one, I guess. Yes, we'll go with that. Okay, so we do multiply, right? See, this one hot encoding matrix is with us, so this matrix we will multiply with the embedding matrix,
right? Because the first time our purpose is to find the embedding matrix first row for the net.
Yes.
So we are first looking for the target word, and that's why we took the one-hot encoding for the net.
Correct. Since the one hot entry for the word ned is this way, right? Somewhere the index for that ned word is 1. So corresponding row from the embedding matrix is referred the weights for that particular center word here. So in this case, this is the first row, right, where we have this neds entry. So this minus 0.018, 0.404 and minus 0.317, these are the initial weights we have used here. So this is just taking it up here. This is a multiplication, so it's the same but just a column vector. Okay. Similarly, so you have taken here which one? Context also, right? No, you're still using this one, right? You're still using this one.
The embedding matrix. Yeah, exactly. We took the same embedding matrix, and now we just exclude our first row of context matrix because we are focused on ned. So I have just circled it with pencil that we ignore the first row of our context matrix, because the word ned is not the context word in this case. It is the embedded word, target word in this case. So that's why we ignore the first row of which is of context, which is for the ned.
Yes.
So but for the matrix multiplication, you might need that, and for matrix multiplication you need to keep the context matrix first and then the embedding matrix, and then you will get the expected output.
I think somewhere here also it's given similar way example.
In example they added like a lot of examples, so we're not able to focus exactly on what they are doing. So the process is,
the same. I will just switch between these two, so we'll see. This is like a colorful diagrams also, right? See the star. This is a newly, right? This is old embedding entry, right? Old context embedding Stark. You already have it, right? This one 018404, right? This is different, old one.
No. Here in this table, right? I can give, in this example, left side star, pimples, zebra, and idiot. All these three word embeddings are given in the horizontal. That 0116, 0.723 minus 0.689 is the word embedding of the first
context embeddings. Okay, for all. Okay.
Context embedding.
Yeah. But we are only interested in these three now. Okay, yeah.
And the next column, next column is the input embedding word, the target word, target or input, we talk both them. So that is put it in a vertical, just to, because each input word dot, we have to compute the dot product with respect to each context word.
Yes, this is just this is just now we got the multiplication, correct? This is the multiplication we got from the center word, and we are multiplying dot product. We are finding the dot product of that word with everything else, like impulse, zebra, and idiot, three context words.
Yeah, and the dot product result is kept in the next column.
Yes.
So the dot.
Correct. So start is the positive context word. So we just got the embedding entry right here, point this one. So this is the entry we just got for the center word ned. So we are using this, we are multiplying this with all the four context words. So there is one positive and three negative, right? Here start is the positive and three are the negative ones. So this is the one. So when we multiply, we get some scalar value here. So this is the dot product for the positive context word. Then respective three dot product values are here. Is everyone clear with this till this point? So we first, based on the center word, we first extracted its entry from the embedding matrix via the one hot entry, right, encoding. So that is this particular we got weight 0.08 and 0.404, right? And then we are just multiplying this center word with all the four context entries. So here, here. So this ned, right? This is the one which we got center word from the embedding, and we are multiplying this with all the four context words. Okay, this is a positive and 3 is negative, and we are finding its dot product. I guess everyone is clear till this point. And then once we find the dot product, we are taking the sigmoid of that value and finding the sigmoid of that dot product value here. So here it is for the positive context word, it's 0.624, and for this impulse negative context word 0.553, and the rest like this. So we got some values. Now if you recall, these are the predictions, right? These are the predictions, and we already know the actual values because we initially said the context word stark is having a target value as 1, but we got the prediction as 0.624. Similarly, the actual values for the negative context word records like pimple, zebra, and idiots, 0 we set, and we got some values. Now we take the difference between these two. So the target minus prediction, right? And we get some value here. They haven't given. Let me check. I think Aditya, you might have done there in your example. So yeah, we have just multiplied. We got the dot product for all. Star, pimples, yes.
Yeah, the first row we subtracted the expected matrix and got the prediction error.
Oh yeah, this one, right?
Yeah.
Why you were 0.37? Okay, same thing you did, okay, right? So same thing, yes, in this metric form, yes. So we got this sigmoid values, right, for star 0.624. Same thing he has put here. Yeah, sigmoid is 0.624. This is the prediction for the context word star, which is positive, and respectively he has just taken here. Where is this? Yes, sir. And we are, as I said, no, like, do we do target minus this one, right, Aditya? Prediction, target minus prediction, I believe.
No, because the expected value we always keep at the negative side, right? So in case if you have a zero value in expected,
correct.
so that becomes whatever is the number is your error. Right?
Yes.
So that's why we keep expected at negative.
Yes, prediction minus actual. Yes. I just saw my notes too. So prediction minus actual, and then we get the error. How much is the deviation from the actual when we predicted in this iteration? Okay, till this point, I hope everyone is clear. And now we take this is the next step right now. So we got the error.
These are in context matrix we have.
This is the current context matrix, right? We are multiplying this error with the context matrix. Okay.
Yes.
Is the derivative part? Oh, no, it's not a derivative, right?
It is a derivative part, because we are multiplying the context matrix with the prediction error with the context matrix. So at the end we need to sum them all. So it is a derivative part, but simplified way.
Okay. So what you have done is you have taken the prediction error, right, and then multiplied its corresponding old context embedding. This you have taken here, and you are multiplying. So
yeah, this is in the portion of the once we summarize add up them, it will become the complete derivative part, but it is in the process of the derivative part, I would say.
See, but how do we multiply? Because the matrix sizes are different, right? This is 4x1 and this is 4x4.
This is a dot product actually. We need to multiply first row with all first.
Oh, this you are multiplying.
Yeah.
Oh, dot product. Okay. I saw this sign. Okay. So this one you are multiplying with this one, right? And then this respective element you are multiplication.
Yeah.
Okay.
Exactly. So it's
if you simply say, right, Yogesh, bottom they have written one formula, the gradient update rule, right? We know after the eta it is dou by delta w. So that is the gradient, right? Whatever is there in the square brackets, that's the delta after eta. I mean, wt minus eta, whatever there in the brackets. So we are computing the whatever there in the bracket actually.
Oh yeah.
That's why we are doing sigma of c positive word dot product of c positive word with respect to input word, and -1 is nothing but it's a target. For a positive word, the target is 1. That's why. And for the negative word, target is 0.
Yes, and we already calculated here, right? Here.
We already calculated above step.
Yeah, this is nothing but for the positive context word, which we -1. So which we already did it here. Yes. Here,
error. Prediction error. Yeah, prediction. Yeah. That is that part. Now, if you see there is a into C positive, first focus on the left part only.
Yeah.
After that error, that whole thing is error. Into C positive is there.
Yeah, C positive.
Yeah, that's again a dot product.
Oh,
so we are slowly computing this. Whatever summation. Next one is context is a summation. Positive word is a single. So, however, we need to again do the dot product.
Yes, and that's why we got this row for the positive context currently, and we have taken the context entry right here. Is that right? Here we have taken the context embedding, right? Yeah, full the context.
Yeah, the initial context. Yeah, it's the same initial context embedding.
Oh, you are multiplying dot product of it all, and plus for the -3 context words. Similarly, you found you did the dot product, right?
Yeah,
So
yeah. Basically, if you see, it's the summation of negative words plus the summation plus we are adding the positive word as well in it. So what I just did is once we got the matrix, we just sum it all because it's ultimately sum of sum, right? So you
yeah,
can see
correct.
in the
These are the
output, yeah,
sum of all the 4 entries, one positive
yeah,
and 3 negative context for entries.
the negative.
So you just
Exactly.
sum
So
it up here, right? This
yeah,
one.
exactly. So just sum it up.
Yeah, and these are the multiplication. Okay. Yeah, this is clear to me so far. Okay. So keep this formula also handy, okay, because this is the one which we are using. This is only one entry for the positive, and since it's there are 3 negative entries, right? So we have this loop here. Okay, now we got the sum, and then we have to update the initial one, right? Again, initial entry.
Yeah. Now we are looking into that formula of WT. So this is the WT part, the initial embedding matrix for NED. So we just took the first row of the initial embedding matrix, which is respective for the NED.
Yes, right.
Yeah.
Minus then this
The
eta
that is
is
yeah,
given. Yes,
learning rate. And then we
and
multiply it with the delta input, the one that we summed it totally.
okay, this is the one which we use it here. Now we are
So
doing
it's
it
yeah,
for the NED, right? NED entry.
yeah,
But
exactly.
we are updating, or which we are here getting the new embedding entry for NED, correct?
Yes,
Okay,
yes,
okay. So you got this one. So the new input word embedded for the word NED is this one. Yeah. So initially we had this, right? Now the new after this iteration, this new embedding entry for the center word is this is the one, right? So far so good.
yeah. So
Every,
it's a stochastic gradient. Like
yeah,
it's always we say like how we update the new weights is we took the old weight,
yeah,
subtract it with the learning rate times the change in the weight. So
yeah.
it's the same formula in different terminology.
Yes, yes. You're done nicely. Yeah. So everyone is good so far. How we come up with here the new weights here?
Hi, Yogesh. Go to a little bit on the first page when we are calculating sigmoid of the last the forward propagation calculation. Here, not that one, the last line.
One second, just scroll below. Okay.
Yeah, this is the one,
Yeah.
embedding matrix and intercontext matrix. But here is like Shankar has added that the first row we have not calculated or something. I missed out here. This is
No, we multiply here, right? First, and then
Oh, okay.
The first was a target word.
First one is a context embedding of the NED itself.
yeah, this one section.
yes, that I got it. The first calculation.
This is the negative context word.
It includes positive and negative, Yogesh. It has 5
positive.
examples.
Correct. Yeah, this is
Out of
positive
that 5
entry.
examples, the first one we ignored because first one is a NED, NED being the context. The word NED also being a context for other words, right? Generally, our context matrix contains all words in both all words will be given with 2 embeddings, being it as a target word, being it as a context word. But when we are taking NED as an embedding or input word, we will ignore NED being a context. Unless NED is also NED follow. NED is also one more NED word also in the context window if it is repeated, but that's not a general case. So when you are taking the input word, ignore that particular entry being a context.
Okay. Got it.
Got it, right?
But
so all the four.
Example. So the 0.116, that is the Stark, embedding for the Stark, word Stark, 0.116, 0.123.
Yeah.
Minus 0.689 is the first target.
First context. First context.
Positive sample.
Positive, yeah.
Remaining 3 are the negative samples.
Yeah, this is the entry from the embedding matrix for the word center word NED, and these are the context word entries from the context matrix. 1 positive and 3 negative. So we multiply, we get this one, and then we subtract it from its actual target to get the error.
I would say one suggestion to Aditya, when you can upload one more because you have this thing, right? Just add the do by do L. What exactly we are adding? You have added that weight update rule at the end, right? Mm-hmm. So yeah, the square brackets portion. If you give the square brackets, complete square bracket portion is what we are computing. That is the derivative. So when it is learning, right, it uses the back propagation. It has a loss function because it is we are doing classification of positive and negative, only binary class classification. That's why we are using logistic regression and sigmoid functions. So at the end, we are for the gradient descent, we have to compute the dou by dou L, the gradient derivatives with respect to the individual words. So already pre-computed formulas, we no need to derive. But at the end, what is like, we are computing the square brackets, which is the delta L or gradient. We use that delta L in the gradient update rule with learning rate. So this square brackets, one time we can add in the up, so that it gives indication why we are computing sigma of C positive product of.
So at the top it should be there, yeah. At the top it should be there.
But yeah, this seems to be correct, right? Everything looks good.
And Aditya put it very nicely. Otherwise, then like a Excel way, that is also good. But
yes,
the examples of yes.
Yeah, but this is good way. Actually, you put in this no, so we now visualize how we can solve the question actually. And then yeah, we got the new embedding entry. Are we also we are it's still there, right? So we got the new entry for the embedding word, like embedding ned center word. Then derivative of this is given here actually. So prediction.
Right. Now onwards, what we do is we calculate the new entries for the context words.
Yeah.
Right. Because we have context metrics. So now we will update those context metrics for the given context words.
Mm-hmm. Yeah. So these are the 4 context words. This is what we got this del, right, above weight in the weight change. We multiply, we get the new context matrix entries for these 4 context words. Okay. Update weights for the context words. Change in the weight. Okay. This is the current one, initial one. Yes, for this one, minus neta and into change in the weight. Can you see?
Sorry to interrupt.
Yes.
Can you share this document so that I think we'll just check forward and backward and see if any queries?
Yeah, this is already shared yesterday by Aditya. If you see the WhatsApp group in like NLP, it's shared. I'm taking from there only.
No problem. I'll take that. Thank you.
Yeah, no problem. So can you repeat again, Shankar or Aditya, this part? I'm just trying to understand this one.
Yeah. So in this part, what we do is, if you go to that sheet of that ma'am shared one.
Okay.
The Excel file. Sorry, that PDF file. Yeah. Scroll down. Scroll down a little bit more.
Yeah.
No, scroll down. Another down. Yeah. So if you see here, we have 2 formulas. Like at the right side, we see now we're taking the derivative of loss with respect to the context word. So now we wanted to update the context word. So what we do is we take the sigma, we take the output sigma and we subtract it with 1 times W. So this is nothing but what we have calculated is our prediction error, right?
Prediction.
So we take that same prediction error, right? And then we multiply it with the input word embedding, right? So we already have our input word embedding with us. So if you look at the input word embedding in the document, so we have this input word embedding for the given input word is nothing but the target word. So this is the input word embedding for the given target word that we have from the initial context matrix, right? Mm-hmm. So because we are still finding the context word, given that what was the initial word embedding. Now we take the product of these two. So if you refer to the above formula, so what we do is again, so this is the way of we calculating the in the original formula, like on the page 2, I have mentioned one formula. And in that formula, we solve for that bracket, right? So if you look at the bracket, it is nothing but the sum of these two. Yeah. So this is the addition of 2 sections, right? So first for the positive, second for the negative.
Yeah.
So in the slides, what ma'am has also done is they have given these 2 things separately, and ultimately we had to use the same formula. So we do the same thing, right? We take the change in the output, so that is delta W in this case. And then we do the regular the way we do it, like we take the word, the initial word, subtract it with the eta times, and then the change in the output. So that's the ultimate formula that we always use to update the weights, is take the initial weights minus eta times the change in the weights. So that's the ultimately we are trying to reflect the same formula.
Okay, yeah. And then we find the new context entries for embedding entries.
New context entries,
And this is just one iteration, right? Now this is first we started with some initial entries, and after this we got the new entries actually. Okay.
Yeah, exactly.
These are the context entries, right? Because these are all the context words we have taken.
Yes. So this is the context entries.
And where is the new entry here? Okay, somewhere here, right? I think here.
That
This is the new
that
embedding
new
entry.
entry is for word embedding. Yeah, that's new
this
entry is for word
word
embedding.
embedding. Yes. So now we found a new embedding entry for the target as well as the context words. Yes.
Yeah, exactly.
So that's the complete one iteration.
Yeah, that's the complete one iteration for target as well as context.
Yes.
So if you wanted to code for this, I would suggest to do both the things parallelly instead of doing one things at the end.
Correct. In the loop, when we take one iteration, we have to calculate both, and then this is the current now, and it will use this one as for the next iteration in the coding part. But in the exam, I think we have to cover till this point to show the current and the next. I mean, after one iteration, what the new entries will look like, right? In these calculations.
Yeah, I think in the exam they may ask for only one word. Like if they ask for context also, because all pre-computed values we can use.
Yeah, I think I'm going to try it on my own because I understood just to get a better feeling, right? So because this is a good question, and if it comes, it will come, I guess, like at least 4 to 6 months also.
Yeah, I think it will come because like she put a lot of efforts in explaining the last session.
Yeah, because she wanted to take it, but during the initial theory part, she might have thought she may not get enough time. So she said, right, she will take it at the end. Yeah, possible, since it's taken explicitly, might be the one candidate. Yeah, but it's a good.
What is the sentence here?
Yeah, sentence here was this one. I think the sentence was, Ned Stark is the honorable man, and they have given this pair here for us. So they have given this pair. So we know Ned is the center word and Stark is the positive context because it is next to Ned, right? So one. But we randomly selected 3 ones. Again, they only gave the 3 words which are the negative context words.
Oh, they provided it in the question. Like
he has this question here. Current negative words, pimple, zebra, and idiot. They only provided. And also this pair also they only provided.
Okay.
And this it also they provided 0.05.
Can you just ping the question here? The one you showed in Notepad, can you just ping it in the chat?
Oh, question? 1 second. I think it's in the PPT. If you see the PPT, PPT 8 lecture, you might find there. Yeah, here it is.
Okay, it's the same question which you are trying now.
Yes, same thing. Aditya has done on paper. So yeah, it's good one. I mean, others too. If you feel this is easy for you, like you can refer this one. Try once with your own. Probably that will give a good feeling too.
One question: this initial embedding matrix and initial context matrix, we have to assume, or it will be there in the question itself?
Question it will be given.
Okay.
In the real world, there are some guidelines how we can choose a random or come up with the initial thing. That's what Madam said.
Yeah.
But in the question, they will give the input embedding matrix and
otherwise everyone's answers will be different. And then again, the staff has to go through everyone's calculation and then find out whether it is correct or not. So I think
Yeah.
This is good. So everyone is good with this? Shall we move on to the next one? I think we almost spent an hour there, but it's good that we covered this one.
So like the output is just like we are trying to find the error and then trying to correct it using the sigmoid function.
Correct. So in each iteration, you will update the weight. So this is the center word, right? This embedding matrix. So here you will update the weight for the Ned. And for the context words, positive and negative. So here you will update weights for the context words because this is the context matrix.
Okay. So in context word, the net is not used, so it is still the same. Again in the
because when there is a iteration, right, where Ned is the context word, that time this will also update it.
Correct.
But now in this particular case, Ned is not the context word, right? It is the center word. So the context words are only these 4. So 4 are updated. Shankar and Aditya, correct me if I'm wrong, or if anybody.
That's correct.
It's correct. Yeah.
Okay.
The learning rate is constant, so we just take a constant learning rate point.
They will give actually. Yes, they will give the learning rate. But I guess if they don't give, probably you can assume that one.
0.05.
But I think mostly they will give again because again, if they don't give and if we assume right, everyone's calculation might differ. So.
Yeah, I think it's good. We'll just need to walk through this. Okay.
Yeah. Okay. Any other? Which other question you would like to take it up? So this one is.
Can Shankar take the Viterbi yesterday's? I love to write. He had posted the answer in the group.
Okay, 1 second.
It will be also like 1 sure question, I believe.
Yeah, right.
Yeah.
And both skipgram and Viterbi can be 5 marks. That's
Skipgram, even I'm thinking skipgram can be 6 marks also.
Yeah,
If they
yeah.
give.
But I just only think like the time which we have, probably it will be tough to complete all the questions. So just be
Yeah,
top of your
Madam
game.
was mentioning ones and zeros only mostly.
Hmm.
Yesterday's PW also I felt like it took time, but at the end it boiled down to few probabilities are zero. So that way, if at least certain probabilities are zero or some, then some computations can be discarded right later, or direct computations.
Shankar, can you forward that again? Because I'm just going through this chain of messages. If you have it handy, I know you have shared yesterday. I'm just checking that too. I know I also replied to your message. I'm just looking into that 1 second.
For topic word embedding, do we have like any examples on that? Because I didn't find any example on word embedding itself.
It's the last one, topic modeling.
Okay, topic modeling. Yeah.
Is that what you're saying?
I was asking like word embedding. Do we have like any examples on word embedding, like except for this skipgram? Because I see in NLP they shared like structure, like how it will be in the exam, right, in the announcement, and they mentioned like the word embedding will have some questions. Do we have any idea? Because I didn't find any numerical on it.
Okay.
Word embedding problem.
No, I'm still trying to understand exactly what is that about. Because there are so many similar topics, right? So I'm trying to
Exactly. It's very confusing to see what exactly.
I think it's only on the neural network. NN, right? Neural networks where we give the word embedding. Is that what you are referring? Where the word embedding is saying.
Yeah.
So there are two TF idea that is going to be there.
Mm-hmm.
And then TF idea is also part of word embedding, where it's frequency based word embedding. And then the other thing which I could see, there are two things, right? Two methods there. And there's a cosine similarity. So these two can be part of a word embedding.
Okay, cosine similarity.
And then this is, okay, so here this is frequency based and there's a prediction based. Prediction based is where we think scriptgram.
Yeah.
So these, my understanding is these three are the.
You're referring to the same one example where there's like a term document and document term that two frequency based, right? Shakespeare plays that example. Is that the one that you're referring?
Yeah, I was just asking like if we have any examples on because I think that comes under vector vector semantics, right? If I'm not wrong, then that problem is on vector semantics. But the word embedding, not sure. The skipgram I know could be
on word vector semantics or word embedding is same. Basically, word embedding means we are representing the word in vector. So both are like it's the same. It's the first to say.
Okay, so they can combine one question on both of them. Okay, that should be possible.
Okay, I found that one, Shankar. So I'm just referring this one. So this is the example, right? I love to write. We have, right? This is the one, and they have given this one in the question.
Yes, emission matrix and the transition matrix are given.
Can you forward the image as well? Can you forward this one?
It is also given in the group.
Yeah, maybe like you can just. We are also trying to search that.
Oh, okay. Wait, let me just mark this.
Just pin it or you can just.
I'll try to.
You can start
reply on this one. Yeah.
Sorry, that is that. Yeah.
Just see, I just replied on that particular solution. Oh, it's still posting. Okay. Yeah, it will just in a minute. It will reply. Yeah.
No problem. We'll check with you.
Yeah. Okay, Shankar, would you like to explain that? That will be easy.
Sure. Here we have given with generally this Viterbi, right? We can be. I mean, it optimizes the HMM model. HMM also does the same computations, but actually it is an extension to the HMM. HMM we will end up in lot of computations. The number of calculations that we perform is almost, if we have n hidden states, and some M observations or T observations, it is n power T, it goes. Those many computations we need to compute to predict any hidden state sequence. It can be post-tagging state sequence, or even HMM not just used for post-tagging sequence. It can be find out for any hidden states. So Vitobi, it optimizes the HMM so that it reduces the computations. For that, it uses it will take the mags in a simplistic way. So we will be given always with emission matrix and emission probabilities and transition probabilities. Emission probabilities is with respect to the, if it is in post-tag, if it observation, probability of an observation given a state. That is what is emission probability. Transition probability is moving from one state to other state. Probability of a state given another state. So that is the transition probabilities. And also usually the transition matrix is called A, and in HMM modeling, when we are training the HMM models or when we are doing the model, there will be initial probabilities of the states that is generally called as pi. The initial probabilities will be given because we wanted to know what is the probability of starting with state VB, if it is a post-tagging starting with the tag verb, starting with 2, starting with n, and we need to know even initial probabilities. So in generally, they will give initial probabilities, transition probabilities, and emission probabilities.
Hello? Okay.
I think 1 hour
Yeah.
completed.
Yeah. It's somehow this also it's 1 hour.
Yeah.
Yeah. Okay, just wait for a minute and then we can continue, Shankar. Recording is still on, not an issue.
And we need to discuss on at least topic modeling is theory based only, application based is what I mentioned, but we need to understand some concepts.
Yeah. Okay, I'm sharing back. Okay. Is this visible now?
Yes.
Yeah, I think. Okay, I guess some people might not know. Let me reply on that message to join. Use the same link.
That is kind of cool, Shankar. Maybe you can just.
Yeah, we can start. I guess.
So in HMM, right, we are trying to predict the sequence given the observation. Right. So here also it's the same which we are trying to do.
Yes, HMM also we will find the hidden state, right? That's HMM. Only thing with HMM is we will need more computations. If our number of hidden states are more and number of observations also more, it takes I said right, n power m computations it takes. If n is the number of hidden states and m are the observations, then it takes very high computations. So Vitobi is an optimized algorithm for that.
But here, like the sequence is, the observation is not given, right?
Observation is given. I love to ride. If you see the bottom, that is the sentence. So this is the, here we are, this particular problem is we are using Vitobi to find the hidden post-tagging sequence. In a post-tagging It can be any hidden state, but generally for when we are applying these models for solving the post-tagging sequence, given this word or sentence, what is the probable post-tagging sequence? Whether I can be predicted as verb or tagged with verb or tagged with to, tagged with n, and starting with that, what would be the post-tagging sequence?
Sequence, yeah.
Yeah, in some cases we get problems like given the weather hot and cold, two states, we need to find, I mean, there are some ice cream problem given right in a class. So based on the number of ice creams, 8 by 1, what is the sequence of the weather? I mean, we can even predict that sequence of the weather. So these algorithms are model, hidden Markov model is generally to predict any hidden states. Direct output state or emitted state is clearly given. That is the observation I love to write. We have some observations. What is the hidden sequence or hidden states? So that we can predict.
Okay, got it.
Yeah. So generally, instead of computing, if there is VB2 NN PPSS, right? There are 4 states given. If we say it will be like at least 16 combinations also will come, right? Even more. What could be the probable post-tag sequence? It can be even. So we have 4 states, we have 4 observations. Generally, it is 4 power 4 if it's all with the HMM. But V2B, we will take like this. So first you put the observations at the bottom. So in the given observation sequence is given. It's always a sequence problem. HMM and V2B solves the sequence problem. Okay, I love to write. That is the sequence of observations. So for that, what would be the hidden truth? So left side, you put all the
states. Yeah.
Like a column, you put all the states. And above each word, actually, we need to put the code because it's a sequence, right? We have to sequence from one state with one observation to next state for the next given observation. And we will move on. And we will finally take whichever is the maximum probability, we will take that sequence in the overall. So V2B computations wise same. So when we take VB to NN PPSS left side, and the first observation is I, right? So what is the probability of, this is simply joint probability of I comma VB, you can think, or VB comma I. So joint probability of is nothing but probability of I given VB into probability of VB, right? So VB here, probability of, because it's a starting state, probability of VB given starting. So that is given in the transition matrix. If you see in the top first row, that's emission, right side one.
Here. Starting to VB, 0.19.
Yeah, 0.19 is our starting probability of post-tag starts with VB. Okay, that's 0.19 into what is the emission I given VB. So in the emission matrix, we need to take what is the probability as I given VB. I given VB is 0.
These 2 are given.
Yeah, these 2 are given. So that's why 0.19 into 0 is 0.
This
Similarly, for the, this part is computed now. So for 2, let's compute for 2 also. So 2 also, what is the starting with 2? So that is, this don't confuse with the word 2. This is a post tag 2. So this column is always post tag. We have a specific post tag for the 2 word. So yeah, that is 0.0043 into what is the probability of I given 2 post tag.
I given 2 post tag. So I given
that is the emission.
Again, this is 0.
0. So the product of this is 0.
0.
Yeah.
I'm trying to highlight to mouse. I think that will help others too. Yeah.
Yes, Yogesh. Actually, that is helping me.
Okay. I'll try. Okay.
So yeah. Now next noun state, NN state. So what is the starting probability? Sorry, I'm frequently using the frequency. It's probability. So the starting is 0.041.
Oh yeah, here it is. Starting.
First row.
Yeah, starting to noun is 0.041. Yes.
0.041 into and I given noun. The probability of I given noun state. I given noun is 0. So that's why we are this probability also. And we call this whatever computations we are doing, we call them as V2B probabilities. We mark it as V1, V2, V3 or V11. So that naming convention is okay, but we call them computations or V2B computations. Next one is PPSS. So what is the starting for PPSS? That is the first row in the transition matrix. First row, last one, 0.067 is the starting.
Oh, this is also there. Oh, okay. I thought only
4 states we have.
Yes. 0.067 is the state transition from start to this state into
start with it. I given PPSS.
Again, this is currently we are focusing on I. So I given this state is 0.37.
Okay. We computed this. So now we come up with 4 frequencies, 4 Viterbi probabilities. Sorry, again, I'm using frequencies, I don't know. So 4 probabilities computed. That's a joint probabilities matrix. Out of this, mark the max one. So remaining all 0, and we have only one value PPSS. Just mark that.
So he just marked
now
like that.
this is marked.
Yeah.
Now we need to compute to the next observation is low, and we need to find out the probabilities for all states. It can be VB to VB, it can be 2 to 2, it can be N to N, it can be PPSS to PPSS. These are the 4 different ways we can go to each state, right? From VB to VB we can go. From starting with VB, we can go to next state as VB. Starting with the 2, sorry, someone wants to. Okay, so let's see similar computation we will do for the next observation sequence love, the word love. So for first one, to compute for the frequencies for VB, there are 4 combinations it can come to VB state. It can be from the previously starting with VB to VB it can come, starting with 2 to VB it can come, starting with NN to VB it can come, or starting with PPSS it can come to VB. And given VB, what is the probability of the word love? Love given VB also we need to compute. So now here, first VB to VB. Actually here we no need to compute the VB to VB, 2 to VB, NN to VB. Why? Because its previous Viterbi is already 0. Otherwise 0 into 0 into 0 we can still take. You got, are you guys getting?
Yeah, we need to multiply the previous state. So previous state at 0. So everything is 0.
0. So we have only one left with one computation, which is PPSS to VB.
0.02479.
0.02479. That's why the last one into what is the PPSS to VB state sequence?
Yeah, PPS to VB, right? PPSS.
Given right side transition matrix.
Oh, VB given PPSS, no? VB, yeah,
VB
given PPSS is 0.23.
0.23. So the 0.024 multiplied by 0.23 multiplied by, we always take the transition probability and emission probability. So that's why transition is 0.23. Emission is VB love given VB, because we are working on love given VB.
Yeah, here love given VB, right? Yeah, love given VB 0.0093.
Yes. So I have put 0.23 into 0.0093.
Okay, this is first term, which is nothing but previous probability. This one. This is the second one, which we just got it from the transition matrix, and this third is the emission for this word. Okay.
The multiplication is multiplication of these 3 is 0.4053. That is the output.
Yeah, multiplication.
Can you explain the transition alone, like VB to PS? Probability of VB given PPSS.
Yes.
Okay, it's quantity. Okay.
Yeah, because now here we are current is our VB, right? Only we are currently focusing on VB. The previous one was we are taking now is PPSS. So from PPSS to VB means previous is PPSS, so current is VB. So VB given PPSS. VB given PPSS 0.23. So here is a 0.23.
One in the second row or in each row, one Viterbi probability takes 3 multiplications. Previous Viterbi into transition into emission probabilities. These 3. And this is done for all the states. Fortunately, the first 3 VB to NN are zeros. That's why we are not computing. Otherwise 0 into 0, 0, otherwise this 0, first 0 is 0 into transition probability of VB to VB into emission probability of love given VB. So it could be the first 0 is actually 3 computations. VB to VB transition, love given VB, and multiplied with the previous Viterbi. So I just directly put 0 because anyway multiplying with 0 is 0. Is that clear? This, if we understand one computation, right, it's the same.
This part. For the... Now we just Shankar just explain only this part. For the current word love, here we just calculated the VB part.
Correct.
Same thing now for
that's here, right? It's a transition table. So I think we also need to mention which is T and T minus 1.
Correct. T given T minus 1.
So I think like my understanding was T always has the start tag. T minus 1 doesn't have a start tag.
No, it's there.
That is for the first column.
Yeah, this one.
Yeah.
See, this time here, no, you're at the start, right? You're beginning, right? So you have to refer this one. So in any state, you are coming the first time, right? So starting to any state they have given. That's what we have used here. See, 0.19 here,
Initial
0.443. Yeah. No, these are the transition probabilities. Emission probabilities are here actually. We multiply. When we multiply with the emission, then the result is 0.
So there are 3 things here actually. One is initial probability, emission probability, and transition probability. Okay.
Yes.
So emission probability, it is like it has a word and tag. So it is the first step. And the transition probability is like which has 2 tags. Okay. So it is the second table. And here also they have incorporated initial probability, which is starting with the S tag.
Yeah.
So that first time is an initial probability.
And again, sometimes I'm just saying because of the yesterday's session, they haven't given the clear separate probabilities for the start, right? Start to that particular tag. But they had mentioned every state has an equal probability. So in this case, we have 4, right? In that case, we can take 0.25. Just remember, if they don't give this start, but they mention take a equal probability, you can take like 0.25 everything. But now they have clearly, explicitly mentioned for this.
That's right. That's the tricky part they can do. Sometimes they give all initial probabilities are equal or some. Otherwise, they will sometimes mention it as pi. One vector they will give pi. They won't embed it into the transition matrix. They give it as a separate entry.
So they might do like a vector like this here, like a 0.19, then 0.0043, right? Then 0.041, and last is 0.06, right? 0.067, something like this they give. So this is the start one. This is for the first tag, second tag, third tag, fourth tag.
No need to consider n tag here. There's no scope for n tag here.
I think that will be one.
Because it's a continuous sequence, right? So no need to consider as end tag.
So one more thing, like in our PPT, right? They have switched the table. Sometimes T comes as a row, and sometimes T comes as a column.
Okay. That is for transition to transition, right? It's always n by n matrix.
Yeah, same here.
But if you found, this is. I mean, given here is initial also given. That's why you will be n by 1 into n. But generally, transition is n by n, because any state can be transited to any other state, or even it can be transited to same state also. Today can be cold and tomorrow can be cold also, right?
So the thing I was just trying to understand is like, is there anything like we say how we decide which is P, which is T, and which is T minus 1? Sometimes the
general convention, at least what we are following, the top columns, right? Top row. Top row is the current word. Left side is this is the given.
Yeah, this is given.
Okay, so emission matrix is given to us, and transition we have to make. How is it?
They will give both give. Only thing
both tables we will.
Yeah, they will give. Only thing, the starting this they might give like this. This is right. Like starting to each tag they might give like this, or they can say each one has an equal probability, and they might not give. So you have to assume depending on how many tags you have. Now in this case 4, so 0.25. But if you have say 5, 0.2.
0.2.
Or they might give like this also, like some pi symbol. That's the convention.
Okay.
Yeah. But they will give this both emission as well as the transition matrix.
Okay. So actually I joined little late. Quick, can you just explain for this one VB? Let's say how.
He just explained VB just now. Yeah.
I see. Actually, I was facing problem to join in Teams.
Okay, we can go with the 2 actually.
Yeah,
so it's the same actually. Let's check with the 2. The Talon will. So now we have to come to the 2 state in the second sequence, second observation. We have 4 probable cases, right? We can come from the previous state being VB to 2, previous state being 2, and again current state is 2, NN to 2, PPSS to 2. So we can come from these 4 different paths.
It's 2 state. Yeah.
Two state. So we need to compute the probability of getting into 2 state given the previous vector B, and also we need to get the emission probability given the, love given 2, because we are now talking about the 2, what is the emission probability of love given 2? I would say first to check both things instead of directly going to the transition. First to check previous, getting into 2 state, previous vector be 0, then we no need to compute that particular path. So that reduces our computation. Also, when love given 2, if love given 2 is what, if by any chance love given 2 is 0, we no need to compute that also.
Yeah, then it will become 0 only, right? Here, complete.
Yeah, but how come I get a value on myself?
Yeah, I was just wondering. Because these are 0, 0, 0 is there. Now we are only calculating, we are calculating PPSS to 2, right here, correct? Now we take this value 0.02479, this is one you took here, into PPSS to VB, right? Like VB given PPSS. So VB given PPSS, no, not sorry, 2, right? 2 we are talking about 2. So 2 given PPSS 0.23. You are not taken this one also. I think you have taken something different, Shankar. So
0.0079.
Yeah, here it will be 0.0079. Oh, you are taken 0.079. That is right. This is also right.
Correct.
And now the third is probability of the emission thing, right? Like love given 2. Love given 2 is 0. I think you just missed this part again. 0.0093 you took. Oh, I think you took the previously like this for the love here.
Yeah, love given VB I repeated actually.
So it should be 0, and then whole multiplication again it will be 0 here.
Yeah, 0.
But it's not a problem because here this is not the maximum, right? So so it will not impact the rest of the calculation. But if somehow if it is a maximum, then everything would be changed in again.
Correct. Okay. So here there is a small, that's a mistake. Love given 2 we have to take, because we are talking about the 2. We have reached to 2 state emission probabilities with respect to love given 2. That is 0. Then that multiplication could have been avoided. So this question, the computation goes wrong actually, because even NN also I took the next state also I took 0.0093 only. Love given
okay. You took the same for all. Okay.
So I
good that we took this one, no? At least I mean it's lot. Everyone's doubts are clear now. But this is helpful. Yeah.
Yeah, can you repeat that for what went wrong? Actually?
Oh, here. Okay, you see here. See, currently we are talking about this 2, right? Or let's talk about NN. Okay, NN. Okay, so when we are talking about this state NN, we are when we can come from this state from either VB state, from the 2 state, from the NN state, or this state. So when we come from these enemies at 0, so multiplication will result in 0. So 0, 0, 0. Okay. But for this, when we come right from the previous state PPSS to NN, okay, so the NN given PPSS is 0.0012. So
okay,
0.00.
No, above.
Oh, here. This is for here. Okay, 0.0012 here. I'm highlighting here by cursor, and this one is the previous one, right? 0.02479. 0.02479 multiplied by this 0.00212, that's the state PPSS to NN, and the third factor to multiply here is emission probability of this current word love given NN here. Now we are talking about NN. So love given NN is 0.0085, right? So mistakenly Shankar said he has taken the same love given BB for all. So that's why, that's the correction.
Okay. Thank you.
But it's a similar way. So he explained these 3 actually, VB, 2, NN. But the same thing we calculate, and whichever is the maximum, we again highlight. Like here we highlighted and use this to go from here, right? Now this is the maximum here. Now for the further calculation, so we move from, take from VB, right? Previous one.
Right.
Is that right, Shankar? Yes. Okay.
Yes. VB to VB also we will take. I mean, for each observation we will compute all these 4, which all paths it's coming. Only computations wise, we will see if previous vector B is 0 or the emission probability being that observation and being in that state. If you see that, then our computations will be simple.
Yeah.
So computational mistakes now only I'm realizing, but be careful.
Yeah, because it's so many calculation, right? It's a small one. Good thing here is that even though you put in this examination like this, I think it should be fine because this is not impacting your final answer, right? Because this is not the maximum. But yeah, this is little error prone.
Yeah. And one more thing to highlight, VB at each state, right? We are getting from 4 paths or 4 states and computed the probabilities, Viterbi probabilities. The Viterbi, what it will take is maximum of these 4, 0, 0, 0, and we have a value coming from PPSS to VB.
Yeah.
So maximum of that, all are zeros and whatever is the value. So we are taking 0.40053 is the output for that VB, Viterbi in the VB state. For 2, it will be 0. For now, for NN also, it will be the computed value, remaining all anyway 0. So max, we are applying max here.
Yeah.
So why I'm saying Viterbi max, there is a forward algorithm which also uses the similar computation. It takes the sum.
Yeah, here it is max, here max. So max of these 4 values. So in that case, it will be sum of 0 plus 0 plus 0 and this computation.
So for the forward algorithm, that's the difference between forward and Viterbi.
So we have 4 terms calculated. So from VB to VB, 2 to VB, NN to VB, and PPSS to VB. So this is one computation, this is second computation, this is third. So all these 0 because these are 0 probabilities. And this is the 4th computation.
So maximum of all 4 calculations, right? So
yes,
there are maximum of all 4.
Yes, there are 4 values. Among 4, we have to pick up the maximum for Viterbi. And if it is a forward pass, they might ask us, Shankar, I believe they might ask us, right? It's the same thing, right?
They might ask the makeup if not here now. At least
yeah, in that case, just instead of max, we have to use sum.
Okay, in the first case, in 4th, we have three values that we have to multiply it and then we have to combine the maximum of 4, right?
Yes, yes. See here 0, right? It is actually a multiplication, but see if you see VB to VB, right? So VB to VB, if you see, it's 0 into something, right? So then it becomes 0. So it's finally 0. But actually it will be like this here. See in the bracket, this is a 1 term here. Since it's all 0, so multiplication results in 0. So he has just put 0 over here.
Okay. It would be like 4, three nested arrays, right?
You can see that way also. 4 actually. There are 4 values because we are coming from this one, right? One of the 4 states to this state. So like this, you can say.
Yeah. Every state has multiplications. Like
so max of. Yeah. I'll try to
max
just
of.
Yogesh, I put it in the chat.
Oh, you all
that formula. Yeah. So one state I put it in the chat of Teams itself.
Right. Yeah. Actually, VB to VB we mentioned, right? That is nothing but Viterbi. Previous Viterbi is what we will call. So every state we are computing the Viterbi, right? So that previous Viterbi, first term is the previous Viterbi, second one is the emission, and even third one you are talking about previous state, VB to VB, the transition probability. Viterbi probability, transition probability, emission probability.
So here we have got the emission probability right here, right? So
yeah, that's
this is 0.
No, that is opposite. Log given VB, generally.
Log given VB. Okay, yeah.
The word given tag. Or observation given state. Yeah. It is W by T. Generally, the terminology to put. Thanks, Gigi. You put that. Just you can correct that log given VB.
Yeah, I'll do that.
Yeah. Since it is 0, its multiplication is coming 0. So this 0, this is 0, and this is 0. Is it clear to everyone? I'll put this back.
Actually, it's simple. Once you understand one computation, everywhere you're doing the only transition and emission. First row is transition and emission because there is no previous Viterbi. And you're carry forwarding the previous multiplications we are remembering, and we are carry forwarding that previous Viterbi into again transition and emission. Previous Viterbi into transition and emission. Only thing is all possible combinations we are taking max of it.
Yeah.
All possible combination to get into that state. 4 states are given means 4 combinations will come. 3 states are given means 3 combinations will come. And like that, how many times we need to proceed? That depends on how many words are there in the observation sequence.
Yeah, here are 4 words. So 1, 2, 3, 4.
Yeah.
I hope they will not give more than this. Otherwise, the more it gives, the more chances of error.
Yeah.
And even the state
more
also.
Than half an hour will take for this, right?
No, basically, if there are
Yes.
zeros, right? It will take some 20 minutes though, definitely.
Yes. And it's a little confusing, right? I mean, at the end, still you might have that one doubt in mind if something is right or wrong.
Yes,
So
yes.
it's better to take like go slow. Whatever you do, just make it perfect, so you don't have to visit back. Because if that happens, no, whatever effort we have put in, right, to build this complete, it might be impacted there too. But yeah, I guess we are good here, right? Thanks, Shankar. Okay.
What is the PPSS referred to?
This is a tag, I guess.
That's
I
one
don't.
tag. That is one tag. I don't know, preposition or
Preposition might be, yes.
Yeah, it's
Preposition phrase.
Okay.
What is it?
Preposition phrase. PP stands for.
Okay.
actually I'm worried about that. If someone gives one good English sentence and give that pen marker table or some table and ask us to tag that, we need to find whether it is adjective, PPSS.
No, in that case, no. If we are not so sure, right, we just take some random A, B, C and continue, because we can't just stay there, right, to get the actual tag value, right, like a 2 or NN. We can say, okay, this has a tag, say A. We assume that its tag is A, its tag is B, and then we can continue.
Yeah.
I think there was some question also related to that. If you remember, I think yesterday's session, right, the first part, we had one such a question where we are supposed to know that, right. Is it part of Gibbs or some I think some concept, right? We have, it's part of that one where we are also supposed to know the actual this one tags. I'm not able to recall, but I have to look for that recording. I guess yesterday's recording.
One final thing in the database, sorry. So every stage you are just marking whichever is the maximum, right? So in the first column, I would say PPSS is the maximum entry. Second one, VB has the maximum entry. Third one, I mean, with my wrong computations, 2 is
No,
the
it's okay. I
maximum.
mean, it's fine. Yeah.
And the fourth one, it is VB again. The top one has the maximum entry.
Oh, here, okay.
So just now, yeah.
PPSS,
so we will.
Yeah.
Our final sequence will be the PPSS. VB all max. Put it in the same sequence that we have marked.
First is PPSS, then second is VB, third is TO2, and fourth is again VB. This is the final sequence.
Yeah.
But it will take 20-25 minutes. It will take. Okay. Any other question? Yeah, it's better to practice. Probably you can take up this example, try on your own, and maybe refer this solution given by.
I would suggest someone take this, correct this one, and post it.
Post it also, yes.
Now we already know we have issue at the second column. I took 0.0093 as emission probability for 2 NN and PPSS.
So only change would be only change would be here. It will become 0 here. So this will become 0. Again, this is 0. So this is 0.
No, this is not 0. NN is 0.0085 is there. Log given NN.
Okay, NN is 0.0085.
Right. PPSS is 0.
Okay, only this 0 and this 0. 2 0. Yeah. Okay.
Yeah.
Okay.
That's what actually. At least they give two or 3 zeros in each column there. Emission probabilities.
That will be better to at least save some time. True. Okay. If we are clear, I think we can move to the next topic. Which example, which topic we can take it up? Anything in mind? This is good actually to have these solutions. Like first one for the skipgram, Aditya has posted a solution, and this time Shankar has posted this one. Similarly, do we have any other problem and solution that we can easily refer and discuss?
One query.
Yes.
So the skipgram negative algorithm which we checked is called as forward algorithm prediction, right? Or
so here we are using the Whittleby actually, but the forward pass, the forward pass, what Shankar mentioned, here we are taking the max, we just have to take sum.
Okay, forward pass is just sum. Okay.
Everything is same, yes.
Yeah. Okay, got it.
Okay.
I saw like a neural language model, right? Even here also computational graph was given. Back propagation and computational graph, neural language modeling, right? We use definitely the neural networks concepts only here. But we might expect one question from that neural language modeling.
Oh, we don't have in this question paper.
Yeah, can we go to the PPT ones? I mean, PPT, if anyone, others, if they have any topic we can discuss. Otherwise, I want at least we can cross-check that neural language model. Even computational graph also, I remember madam was mentioning one of the computational graph here.
neural language, neural network and neural language models. Yeah, she just skimmed through this one. Neural unit, this is what we know already.
Yeah, these are
Okay. This is just a demo, right? Okay, suppose
this is a sigmoid. I mean, I'm just thinking which type of question can come from this module. If you scroll down, there is one computational graph also given.
Okay.
I'm not sure if simplistic questions like that also, if this like this may come.
Perceptron. These are the basics, but just looking for that any example they mentioned, like you saying. Feed forward. Theory part. Did you see, Shankar, that example? I mean, it's there, right, in the PPT? Yeah, neural language models. Okay. The same thing which we do it in DL now, right? Is this something, Shankar, you are talking about? It looks like this is a simple example. A plus 2b, C into A plus 2b.
Yeah, I think this is the same example I was talking about. Because here we have this computational graph, right?
Yeah, because it has a computation graph used made by this.
Shankar, you're speaking, you're on mute.
They given weights 312.
Yeah, so yeah, this one only. So I'm not sure what sort of question from this topic.
So I think my understanding was she just took a toy example to explain us the feed forward and then backward.
Oh, this is just simply same as we discussed in the DL also, right? This is the same thing. Yeah, same thing.
She was mentioning it's a toy example, just for us to understand.
Yeah, it's the same thing. C into A plus 2b, right? A, so B 2b, then A plus 2b, and then multiplied by C here. So that's the final our equation. Then forward pass. So they might give some values here. ABC. We get the loss. Yeah, this we know right now, chain rule for the back propagation. See, this example is given actually. See, for the same values, this was given the back propagation also, the derivation part and back propagation values too.
Yeah.
For each level, the derivation part and what is the value and all. Now this is the loss, right? The back propagation in the red. This is the forward pass in green. In red is the backward pass.
So one question on this part, like we always need to derivate with respect to the L and then the last function L. Yeah.
Yes.
Or is it it's always mandatory, like?
Yeah, we have to go till this point here. So here dl by de, then if you go here again dl by dd, but you can't directly take it. So you have to go like use this d by dl dd by de by dd into this chain rule you have to apply, like dl by de by dd to calculate the yeah.
And can't we like say like L equal to CE, then we again write L equal to C times of D plus A, and then again D is 2B, so can we expand L like that and then do the derivative?
Or like if you do that, right, you will doing it for suppose A, B, C. If you want to compute, again you will be repeating all the things. So this change simplifies use incremental way. You remember your previous this thing and you use that. So that's the computations wise, it makes your easy. Otherwise, every time, every attribute, if you want to derive from the, last equation we already know, C into A plus 2B, right?
Mhm.
L equals C is nothing but C into A. What if there are more number of parameters are there? Every time you wanted to do all partial derivatives to, at the end,
Okay.
we get the weights and biases, right? Those are the parameters.
Mhm.
So dou L by dou C, for example, dou L by dou C. In this case, L is already a direct C you are seeing. But what if it is a big equation of, then you need to compute all the terms every time. When you are doing dou L by dou B also you need to compute. When you are doing dou L by dou A also you need to compute.
Okay, so expanding is not a good idea. Okay.
But if you want now, in the DL session, Shankar has explained one problem, like from like both forward and backward pass. I think if you look at that recording, that will be good. It's the same thing.
Okay, sure.
Yeah.
Right. So any idea like where can I find that recording?
I think Manoj shared, right, somewhere. Let's see in the chat actually. In the DL group, we have to find out that because I remember Manoj has shared the link for the recording as well. Or probably check for his blog. Blog. See if he has uploaded there. Generally, he puts everything over there.
Yeah, I'll check. Yeah, thank you.
Because he has given in like a full detail the problem statement. We solved one problem, right? Yeah, that will be easy.
This Pravina's one, Pravina.
Oh, I think they have an exam right now going on, PGM something, right? They.
Yeah,
I remember Manoj said he has exam now. Till
Yeah,
11th.
they have an exam. It's
Yes.
just got over.
Oh, okay. 11:30. Yes.
Yeah, 11.
Yeah. Because Manoj is also planning to set up a session for DL, and then we decided, okay, we'll have NL now. So once he's available, he can share the DL session link maybe in some time.
Okay. This NLP Veena session, something is I can see actually peer sessions in the peer session, right?
I just pinged in the chat. Maybe you can look at it. The team's chat.
In the link what is shared, actually if you go to this group subject, you will find there are links.
NLP recordings, if you're talking about, I am recording those sessions and I have kept in this shared drive there. You can take it from there. So today is our third session. So any other topic, guys?
Yeah, and if you scroll down, I'm not sure this neural network, neural language modeling.
Okay.
This question, I'm not sure.
Anything regarding neural language?
Any other question may come, right? Parameters, how many number of parameters?
Backward pass again, but here the multiple layers. Oh, neural language model. Okay, that's what you were saying. No, now the embedding started here.
No, we might be using word embeddings, but any specific problems?
Okay, neural language model here as well. So is it a prediction here? Because t-1, t-2, training the language model. But I remember when in some example, right, she was explaining, we use the embedding here, right?
Yeah, we use the embedding. And that's why she covered first the vector semantics and embeddings.
Embedding part,
which is required for the neural language models. Otherwise, beginning she covered n-gram-based language models. Then this neural language model, I'm just thinking what type of questions can come. Because in the previous papers, we did not find much, right? I'm not seeing any problems.
Problem here. Actually, yeah.
Photograph is only can be there. I'm not sure whether she will do that.
Yeah, these are the words, right? So for the word for, this is the embedding here. And then for the word all, the embedding is taken from here. And these are the embeddings fit to the neural network that I remember.
Right.
Correct, right? Yes. Yeah, I think there is no example. Even I don't remember any such example is taken there.
I think then we are good. If we don't get any, by any chance, if any question comes, I'm expecting that computational graph may, but that is same concept for DL.
DL, yes.
Yeah, maybe I think we can just brief whatever we have solved, right? Or what are the questions we have solved, we can just solve. Because it's just questions only. Right? What is the topic we are expecting questions?
Yeah, I think we covered last two sessions. We covered a few topics and we solved some questions. There were some questions like a skipgram and little else we wanted to revisit, so we did today. But any other you guys think? I mean, I have this question paper open here. I guess yesterday we were almost here. If you guys want, we can go over this again. Otherwise, we can close the call and we can continue self-study also.
So what is this?
Oh, these are the previous year question papers.
Okay.
Yeah, we solved it actually. We checked all the questions mostly and we tried to solve. Yeah.
Any idea on what could be the LDA part questions? Because I think it was not there in the last year. So, do we have any idea about LDA? I know it's quite difficult topic.
LDA, there is no example taken also, right, in the class, because I have gone through the theory part.
Okay.
It is not like what you're saying, it's not only theory part. I think get a grip of that. There's no problem.
Do we expect empiricals from LDA? No, right? That's right.
I have no idea because I don't see the example, but since it's in syllabus, we had this syllabus also.
Application,
right?
Application based problem is what we can expect from the LDA. That's what LDA means. Why we have two Dirichlet distributions, distribution over distributions, two multinomials, and what we do, what are the two different distributions we are going to compute. So theoretically, we may need to explain. Even simplex visualization also there, how we will visualize the things when there is the distributions. And there is a sampling. So theoretical or application based question is what yesterday I recapped again the eighth session. So I just quickly gone through that. When I was mentioning we can get a theory application based question. So we need to understand why what is the multinomial distributions used, Dirichlet distributions used. So there we do two distributions we compute, like it's basically topic modeling. The entire thing is called topic modeling. One, the number of words in the topic, the distribution of words in the topic, and topics in the document. So the distribution of topics in the document.
Yeah. Where is this one?
That's like only the difference between topic modeling and clustering. So
clustering is different and topic modeling is different, you mentioned. Yeah. But however, topic modeling can be used in the cluster.
Yeah, the topics document can be divided into multiple topics, right? Oh, not the document, but we can have a topics, set of topics, and each document having these topics, right? One or more topics.
Yeah, generally, number of documents will be given, and number of documents contain number of words, and they will say how many different topics we can visualize or compute from them. So generally the topic count they will give. System does not know what is the topic name. So based on our distribution and probabilistic algorithms, we will this LDA modeling, LDA, right? It will categorize these things into topics. Topic one, this is based on the probability count, probabilities and probabilities of that words being in that topic or being that document. And later on, some human being will come. This is the two different distributions within the topic. What is the word distribution? T1 distribution is given, right?
For each topic, T1, different words.
What is the distribution?
Yeah, and what's the frequency? This is the frequency of each word, right? Is that the one?
Yeah, distribution. Overall, what is the distribution, of words? So that is one multinomial distribution. And if you see the left bottom, if you see the down, in the same.
Here.
There is a document.
Correct. So in this document, now we have different topics and the distribution of this. Okay. So now here we have taken three topics, T1, T2, T3. So we are seeing 3 bars. So in a document D1, how is this T1, T2, T3 topics are distributed? One. And in each topic, how words are distributed? That's the 2. Yeah, the example she was explaining, right? I had to go through 3-4 times actually, because it's like all the similar terms.
I'm also a bit not clear. I went once and I also went to one of the YouTube video, but it's distribution over distributions. So multinomial distribution and Dirichlet distribution both comes. LDA means latent Dirichlet distribution. Dirichlet.
The example she gave, right? Some I think here it might be.
Yeah, I think everyone can go through this and at least we will copy something from the PPT
only. Right? Yes, PPT only. Any other topic? So this is the third session. We already covered other topics. So the idea was to just focus on the topics which are not covered instead of repeating the topics. But any other queries? Otherwise, we can close the call and we can go back to studies,
Yeah.
because it's only less than a day now, right? Tomorrow 9:30 or 9 o'clock. What's the
9 a.m.
9? Okay.
For DL, we don't have same as like NLP, right? There is no like all the questions solved in a question bank, right? For DL, it's kind of much blank, right?
No, DL, I think we have the questions. What Manoj and someone also helped him. So what they did is they took the questions, created a separate document, and then many people helped, like solving that actually. So we also had the sessions that Manoj organized, and then we solved the question, we discussed and solved the questions, and we also updated in the same document. So today we will do that. We will combine all those things together into a single PDF, and then we can share. So we will have all the questions with answers wherever we have that we can refer.
Okay.
But yeah, how we what we discussed and the solution part, you have to go through the recording then.
Okay. Thank you. Or anyone of your friend gave exam for PGM, and how was the experience? Anyone have shared with you guys?
Oh no, PGM just now they completed, right? I think 11:30, half an hour back. We don't know.
Yeah.
We have to pull someone and ask him to join this call.
Yeah, Pravina.
Yes, we will get to know.
Shankar, are you checking with someone? Is to get some? Yeah.
We can do Manoj.
I checked with one. Okay, she said like the proctor was saying to them to focus the secondary camera on the keyboard or the hand where you're writing.
Oh man,
something like that.
So we have to focus on other things, not than what is really required. Right?
Yeah, kind of not sure, but she said like not for everyone. 2-3% only they said, and sometimes they said see straight if somebody is making left or right or something.
Let me check with Manoj if he's available.
I think meeting lost again.
Yeah. Just 1 hour.
If it would be really better if we can get someone from PGM to tell their experience, right?
Yeah.
It was difficult.
I have asked Manoj. Let's see. Shankar, did you ask someone else also?
No, I did not ask.
Okay. Let me stop the recording.